Hey Maya, how are you?
Oh, hi. I'm good. How are you?
I'm doing fine. Yeah, long day today. How was your day?
Yeah, very well.
Mm, let's see. So, do you have any questions so far?
Um, yes, what's it called? It was alcohol dehydration. Yeah,
Okay. Yeah, alcohol dehydration.
yeah.
Yeah. So for alcohol dehydration, you know that you have this reaction when you have an alcohol in your reactant, right? And it's probably gonna be um a secondary or tertiary alcohol. And the reagents that you see on the arrow are going to be some kind of acid. It could be like H2SO4 most likely, or H3O plus under heat. So if you see a delta symbol like that, or a triangle symbol, then that's most likely going to be alcohol dehydration. Or instead of seeing that heat, you can see high temperature like between 170 to like I think 180 degrees Celsius, some high temperature. Right? And your product is going to be an alkene, a double bond. Right? And the mechanism that it goes through is an E1 like mechanism. Okay, so let's look at an example problem. Let's say we have something like this right here, where we have an alcohol right here, and we put that through acid and heat. Okay, so you notice how we have a strong acid here, H2SO4.
Mhm.
That strong acid is going to look for the most basic atom, which is going to be this oxygen right here of the alcohol, right? That oxygen there with the alcohol has two lone pairs of electrons, which can, oh, let me disable the waiting room so other people can join. Okay, there you go. So that alcohol oxygen there is going to get protonated by the strong acid. And once we do that, we are going to form this oxonium ion here, OH2 plus. So is this a good or bad leaving group right here? The OH2 plus.
Is it bad?
So when it leaves, right, it's gonna leave as a water molecule, a stable neutral water molecule. And if it leaves as a stable water molecule, it's going to be a good leaving group,
Oh, okay.
right? Before it was a bad leaving group because before it was just OH. If it leaves as OH, it will leave as OH minus. This is very unstable and very reactive. So we converted this bad leaving group into a good leaving group right here.
Oh,
Right.
okay.
Okay. So for SN1 and E1 mechanisms, do you remember what the very first step is going to be?
Um,
Like once we have this good living group, that good living group can just leave by itself. So let's just kick that out, right? When that happens, what charge do you think this carbon is gonna have right here that just lost the bond?
like 12.
Yeah, positive charge. That's right. And whenever you have a carbocation or a positive charge, do you remember what step you always have to look out for?
Don't you, what's it called? You move a bond over to that one?
Yeah, to make a more stable carbocation, right? Like there are not the
Yeah,
stability of carbocations like primary, secondary, tertiary, and then the more substituted the carbocation is, the more stable it's gonna be.
yeah,
Right? Right now, this is a secondary carbocation, but if we look to like the right or left of it, we see that it can become more stable if it moves to that more substituted position, right?
yeah,
So to do that, you know how that carbon has an invisible hydrogen?
yeah.
That invisible hydrogen is going to move onto that carbon right there. This is called a hydride shift. Okay. And
Mhm.
when we do that, this carbon here gained the hydrogen. This carbon right here lost the bond, which is why it's going to be a positive charge right there now, right? Because this carbon here used to have four bonds, one, two, three, four, but now it only has three bonds, one, two, three. Since it lost the bond, it has a positive charge, right?
Kind of forgot, how do you know when to use the hard drive shift rather than the alkaline shift?
Oh, right, right. So, let's say we have this carbocation right here. Whenever you form a carbocation intermediate like this, you always have to stop and look at the nearby carbons here and here and see if it is more substituted and if it can become more stable. It doesn't want to go to the right side because that's going to become less stable. But on the left side, it can become more stable because you notice how that left carbon there is more substituted.
Mm-hmm.
But does this carbon here have any hydrogens?
No, no,
Yeah.
yeah,
So
no.
since it has no hydrogens, we have to do the alkyl shift, where we're going to move one of those methyl groups to that carbon right there.
Okay, yeah.
Uh-huh. Where you notice how this carbon here lost the bond because before it had four bonds, now it only has three bonds and a positive charge. This carbon right here that used to have a positive charge gained the bond, which is why it's now neutral. Right?
Okay,
So this is an alkyl shift. Okay. Now, once we have this most stable carbocation intermediate, we have to look at the um beta hydrogens. So the beta hydrogens are going to be one carbon away from the carbocation, right? So this is one beta hydrogen, that's the other beta hydrogen, and this is the other beta hydrogen. Let's say this is A, B, C. Which beta hydrogen do you think is going to form the most stable double bond, the most substituted double bond?
see.
Oh, what was that?
Oh, see?
Yeah, C, that's right. It would be this hydrogen here because that would give us the most stable double bond. Where the base that we're gonna use is the conjugate base that we made in the very first step. Because you know how the very first step was to protonate the alcohol and then kick out this conjugate base right here?
Mm-hmm.
That conjugate base will come in now to then deprotonate that beta hydrogen, make a double bond right there. And that gives us our most stable double bond right there. Does that make sense so far? Like how this double bond was made?
Yeah,
Uh-huh. Do you have a tablet or an iPad with like note-taking ability?
yeah.
Uh-huh. Do you want to connect this so then we could use the whiteboard feature and then I can give you practice problems and then I can see like you work through the mechanism and then see what you have so far.
Wait, I don't know how to connect the iPad though, but
Uh-huh. Oh, the iPad
uh,
have Zoom.
oh, yeah. Okay,
Uh-huh.
hold on.
Yeah. Uh-huh. So then you could like practice while working through it and then I can see like where you need help on and then we could like work through those.
Okay.
Mhm. And also, for our tomorrow session, I'm gonna have the reactions planned out for us, the practice problems and stuff like that, on what he basically went over, and also like what he didn't finish as well.
Okay.
Oh yeah, when you see the audio, join with no audio, so then it doesn't have an echo.
Oh, shoot.
Okay.
Okay. See- Okay, practice with this problem here, predict the product, and draw the arrow pushing mechanism as well. Let me know when you get stuck.
Okay.
And what would be the charge of this oxygen right here that gained another hydrogen and now has three bonds?
Is there a negative charge? No,
So
positive.
yeah,
Sorry.
positive charge. Yeah, positive charge. That's right. Uh-huh. And now we just created our good leaving group. And if it goes through an E1 like mechanism, then that leaving group will just leave. And this alcohol right here with two bonds is neutral. There's no charge on this
Oh,
oxygen right here. Right. So for the charges, oxygen with two bonds will be neutral. Oxygen with three bonds, one, two, three, will be positive. Oxygen with one bond will be negative.
okay. Is this a hydroid shift?
Yeah, that's right. Hydrate shift is gonna happen next. Yeah, there you go. That's the hydrogen that's gonna move.
This the end product?
Right. So after this hydrogen moves to that carbon right there, this carbon here, what charge would that carbon have right there? Since it lost the bond. Before it had four bonds, one, two, three, four, but now it only has three bonds. And what kind of charge?
Positive?
Yeah, positive charge because it lost the bond. So let's draw that positive charge right there. Now, locate your beta hydrogens. Draw out your beta hydrogens on all the beta carbons. That's one of it. That's the other one. And here's the other one. Now, which beta hydrogen is the most substituted beta hydrogen?
This one?
So this beta hydrogen here, how many other carbons is that carbon attached to? This one right here.
Um, Two? Or you mean,
Yeah, so this carbon here is attached to two other carbons,
yeah,
one and two. This carbon right here, how many other carbons is this carbon attached to?
one,
Yeah, one. That's right. And how about this one?
three,
Three, yeah, one, two, three. So this one here is the most substituted
um,
hydrogen. So that's the one that's gonna get deprotonated by the HSO4 minus. Where these are minus charges here, the HSO4 minus, because um before it was neutral, but once you do this protonation step, we have another arrow that's gonna come like that to give that HSO4 minus charge like that. Where this HSO4 minus charge can now come in and grab that hydrogen and make a double bond right there, the most substituted double bond.
okay.
Uh-huh. So let's draw those arrows and the product. Yeah, that's right. This is the final product where the arrow that to get there is that this HSO4 minus grabs that hydrogen, and then this bond between carbon and hydrogen, you drew the arrow correctly, moves and makes a double bond right there, right?
Okay.
And then our H2SO4 acid catalyst gets reformed, right? Because before we had a HSO4 minus, but that HSO4 minus got reformed back into H2SO4 because it just grabbed the beta hydrogen here. This extra hydrogen there gave that HSO4 as the second pair of hydrogen, the second hydrogen there. Right?
Okay.
Okay. So let's try a similar problem here. Okay. Let's try. Yeah, let's try this one.
For this one, would it be E1?
Oh, well, what was that for this one? Oh, what was the question? Sorry.
Oh, sorry. Is it E1?
Uh-huh. So it's gonna be E1 like where you know how what kind of functional group do we have in the reactant here? What's the functional group in the reactant that we have? Like what is this functional group here?
Oh, um, that's an alcohol,
Yeah.
so
Uh-huh. We have
so like
alcohol,
yeah.
strong acid, and high heat. If you have alcohol, strong acid, and high heat, this is a big sign of the reaction alcohol dehydration. So it's the same reaction we did previously, but just a different molecule this time.
Okay.
Mhm. And don't forget the bond between that H and the HSO4 goes onto the HSO4 to give that HSO4 a negative charge as well.
Will I get points off if I go like right these things?
I think so. Yeah, these can
Oh,
count as minor points for the mechanism.
okay. Would this be an alpha shift this
Hmm.
time?
Yeah, yeah, an alkyl shift. It will be. That's right. And when you drew out this thing right here, the H2SO4, that's neutral by itself. The thing with the negative charge is just HSO4 minus. Only one
Oh,
H.
okay. Sorry.
No, it's okay, it's okay. You make the mistake now, so you learn from it and you
Yeah.
avoid them during the exam.
Yeah. It's because in Chem 118A,
Uh-huh.
the last 4 weeks, that was when I struggled.
Oh, the last 4 weeks of 118A with all the SN2, SN1, E1,
Yeah.
E2 mechanisms,
Yes.
reactions.
I think the TAs are being too nice. They gave me too many points.
They
I did not deserve it, but so can I just take any from like this side?
Yeah, any of those methyl groups. We have three methyl groups, so just choose one methyl group to move onto the carbocation.
Okay.
Hmm. Right. Now you moved one of the methyl groups there. Which carbon lost the bond?
Mm,
Uh-huh. Yeah. So since that carbon lost the bond, that will have a positive charge now. Right. And once you have your most stable carbocation intermediate after the rearrangement step, so either hydro shift or alkyl shift, in this case, we did an alkyl shift. Now you look at your beta hydrogens and then choose the most substituted beta hydrogen to do the elimination reaction to form the double bond. So now let's label or identify where our beta hydrogens are. Yep. Uh-huh. Yep. So that is a gamma hydrogen. That is too far away.
oh, is it just these two?
Those two and this one right here.
Oh, yeah, that one. Okay.
Uh-huh. Now, which one of these beta hydrogens is the most substituted?
This one?
Yeah, that one. That's right. That's right. So bring in your HSO4 minus to finish the mechanism and product. Right. And then after that arrow, what other arrow
Oh,
happens
yeah.
that makes the double bond? Yeah, there you go. There you go. Uh-huh. Yep. That is it. That's the final answer. That's good.
Okay.
Uh-huh. Any other questions on alcohol dehydration?
I'll probably just practice this more
Yeah,
this
I'll
one.
come up with more practice ones for you to try out on your own.
Okay.
Uh-huh.
Thank you.
Yeah, yeah, no problem.
Um,
Any other reaction mechanism?
maybe hydrogenation.
Hydrogenation. Okay.
Yeah.
So hydrogenation is basically when you react an alkene, let's say the alkene right there, with H2 and some kind of catalyst, like it could be PDC, PT, some kind of catalyst, like a metal catalyst, right? This alkene right here, you know how the alkene carbons have one hydrogen right there already?
Mhm.
Right. Let's say those are the original hydrogens. And let me color code this H2 as blue. When we do this reaction, we are going to add the H's from the H2 to both carbons of the alkene. You know how these two carbons here are the carbons of the alkene,
Yeah.
right? Those two carbons there gain a hydrogen from the H2 right there. Right? Where the mechanism, you don't really need to know this, but it goes something like this. It's good to know that they are syn addition though, like they add on the same side. So if this was a wedge, then this would also have to be a wedge because this mechanism does syn addition. And this means that the hydrogen or deuterium, which you might see, adds on the same side. So if one adds as a wedge, the other one would also have to be a wedge. Right? So the mechanism is something like this. Let's say your metal catalyst is down here, and there are a lot of hydrogens on that metal. When you bring your alkene near this metal, I think it goes something like this, where the wait, let me double check this mechanism really quick.
Okay.
I see. So one of the hydrogens here is going to attack the alkene, and then the other side of the alkene is gonna go attach onto the metal. When
Mm,
that happens, we get something like this. Let's say the hydrogen that attacked is purple. That purple hydrogen is there, and then the other side of that alkene is attached to that metal now,
okay.
right? And then another hydrogen is just gonna attack that carbon, and then that bond is just gonna go onto the metal. Like this mechanism won't be tested, but you notice how it's forced to attack on the same side,
Mhm.
right? That's why this is syn addition. So that's why if that is wedge, this would also have to be wedge as well. Or if it was dash, it would also have to be dash as well. And this is more important for chiral molecules. Right now, this is not chiral, but just know that it adds onto the same side, which is syn addition. Right? And also, it will add onto the less sterically hindered side as well. So let's say we have something like this, an alkene here, this R group there, and another R group right here. And we put this through D2 PDC, right? D here is just an isotope of hydrogen. Where you know how for these products here, you could just draw out like this product without drawing in the hydrogens because hydrogens are invisible. They are optional to draw out.
Mhm.
When you have D2 here, you have to actually draw out that D. You can't make that invisible.
Okay.
Right? So we know that one D is gonna attach to this carbon, the other D is gonna attach to that carbon, and we get rid of that alkene. But which face is it going to attack? Will it attack the top face or the bottom face? Would it go attack on the top side where the wedges are, or the bottom side where the dashes are, based on what is around in the molecule?
Top.
The bottom? Yeah, that is right because of something called. Do you remember that factor?
Okay.
Steric.
Oh,
Uh-huh.
Eric Fingers.
Yeah, steric hindrance. That's right. The top side here, the wedges, there's too much steric hindrance. Like it's blocking the D's from attacking the top side, right? Like there's too much space there. But it can go on the bottom side because you know on the bottom side the dashes, there's nothing there. That's why there's
Mm-hmm.
less steric hindrance there.
Okay.
Right? Okay. Now that is the uh stereoselectivity of that, and also let's say we have something like this. If you have multiple alkenes, right, the hydrogens will add onto all of the alkenes. They will reduce or hydrogenate all of the alkenes. So what we could do is just get rid of all of the alkenes like that. Where what happened to the alkenes? Like what got added and what got removed?
Added hydrogen.
Uh-huh. Yeah, the hydrogens on all of the alkene carbons gained a
Mm-hmm.
hydrogen atom. Do you see any chiral sensors here?
Mm, is it on the first hydrogen on the left?
Um,
Or
let's say this is A, B, C, D. Are any of these chiral centers? And do you remember the
and
definition of a chiral center?
I don't think I remember.
So that chiral center is going to be a carbon with four different groups attached to it.
Oh, yeah. Okay.
Different groups. Where the only carbon that has four different groups attached to it is this carbon right here. It has a methyl group, this CH2OH, this hydrogen, and this whole group right there. Those are four different groups attached to the carbon. Right? Why is this carbon here not a chiral center?
And it has two metals.
Yeah, it has two methyl groups, which are the same exact groups. So that is not a chiral center because we need four different groups attached to the carbon. This is not a chiral center because that has two hydrogens, two hydrogens, two hydrogens. This right here, the purple star, is a chiral center because there's four different groups attached to it. Uh-huh. Where you notice how when we do hydrogenation, we said that it could either attack on the top side or bottom side, right?
Mm-hmm.
Let's say that this hydrogen here attacked on the top side, making that a wedge. If that became a wedge hydrogen, that forces the methyl to become a dash. Right? But we could also have another product where if the hydrogen was attacked on the backside, it became a dash hydrogen that forces the methyl to become a wedge. So these are the two different products that we see here. Does that make sense?
Okay. Yeah.
Yeah. And do you know what these are to each other? Like, what's the stereochemistry relationship between these two molecules?
Oh, like if it's R or S.
Oh yeah. Like one is gonna be R, one is gonna be S. So what are they to each other if all of the R and S's flip? Like, are they gonna be?
Enantiomer,
Oh, what was that?
enantiomer.
Yeah, enantiomers. That's right. Enantiomers. If all of the chiral centers flip, they are enantiomers of each other. Right? If
Mm-hmm.
some of them flip and some of them stay the same, they are
Diastereomers.
yeah, diastereomers. That's right, diastereomers. Huh? That's good. Do you want to do practice problems on this hydrogenation or move on to the next reaction?
We can move on.
Okay, okay. So, do you want to go over the reaction that has like diastereomers instead of enantiomers?
Yeah.
Okay, let's do that. So, uh, the other reaction is gonna be addition of X2, where X is probably usually Cl or bromine. Right,
Mm-hmm.
to alkene. Okay. An example, let's say a simple example, Cl2, and then some non-nucleophilic solvent. Because there's two cases of this reaction, non-nucleophilic solvent and nucleophilic solvent. Let's just focus on the non-nucleophilic solvent first, which does nothing in the reaction, which is just CCl4, or you could just see Cl2 by itself with no other thing on it. You know how previously when we worked with oh wait, we didn't even go over HX yet. Oh, let's go over
Oh,
that first before we go over this
okay.
this reaction here. Yeah, because
Okay.
that's important. Yeah. Addition of HX, where X can be Cl or bromine usually, to alkene. So an example here, HBr. So we know HBr is a strong acid, then think of the alkene as a strong base. But there are two carbons of the alkene here, so we have to decide which carbon is gonna grab the hydrogen. First, which carbon of the alkene is gonna give us the most stable carbocation intermediate? Which carbon is the
Oh,
most substituted?
last one.
Yeah, the left one right here, because there are more groups around that carbon. So since we want a positive charge here, we want this carbon to lose the bond. If we want that carbon to lose a bond, that means that the other side of the alkene, this carbon here, is going to get protonated. That carbon is going to get protonated by the HX there. Right? Where you notice how this carbon here gained the hydrogen, which is that hydrogen right there.
Mm-hmm.
This carbon here lost the bond, which is why it has a positive charge right there. And we also kicked out the Br minus, where that Br minus is just going to come in and attack that carbocation right there. And that gives us this product here. Does that make sense?
Yeah.
Okay, so another example here, let me give you that on the whiteboard.
Okay.
Okay, let's say we have, okay, predict the product and draw the arrow pushing mechanism for this reaction here.
The hydrogen goes here.
So we want this carbon to have the positive charge rate because it's the more substituted one. That means that we want this carbon here to get the hydrogen. So this carbon here
Oh,
attacks the hydrogen right there. The hydrogen never attacks anything. It's always the one
oh,
being attacked.
okay.
And when that happens, this bond between hydrogen and the X gets kicked off and kicks out the X minus and gives the X. Yeah, there you go. So
You're
before,
like that?
yeah, yeah, that's good. But then the Cl minus does attack the electrophilic carbon, but this is the common like thing that a lot of people forget about. Whenever you form a carbocation intermediate like this right here, do you remember the step that you always have to look out for before attacking it?
Um,
Can it go anywhere that is more stable?
Um, mm, like, could it be on the left side too?
Yeah, it could be on the left side here. And how can we move that
Uh,
to the left side? What is that step called?
a hydrogen shift?
Yeah, hydride shift, because this carbon here has a hydrogen, which can move to that carbon to do a hydride shift and give that carbon a positive charge. So let's do that.
Okay, so we'll go here.
Uh-huh. That's right. Hmm.
And then this is positive now.
Uh-huh. That's right. Because that carbon lost the bond and now it has the positive charge where it's more stable and happy at because it's more substituted. And then you bring in the Cl minus to attack that positive charge. This is the step that a lot of people forget about, like that hydride shift or metal shift.
Okay,
Yeah, that's a common mistake. That's a common mistake. Uh-huh. Yeah, and this is your final answer here.
okay,
Mhm. Want to do one more practice problem on this concept?
yeah.
Mhm. Let's go. Let's go. Let's do. Okay, let's try this one.
So this carbon, like this one, like wants a positive charge.
That carbon there wants the positive charge, which means that it wants
Okay,
to lose a bond. And if it wants to lose a bond, that means the other side of the alkene grabs the hydrogen, not this one because it wants to lose the bond. That's right. That's right.
okay,
And then what happens? Yeah, there you go. Kicks out that
okay.
X.
Did we do a metal shift?
Yeah, uh-huh. We do a metal shift.
Okay,
That's right. That's the forgotten step. A metal or hydride shift.
okay. So
Uh-huh. Nice. Nice. That carbon there has a positive charge because it lost the bond. Before, that carbon had four bonds, one, two, three, four. But after the metal shift, it now has three bonds and a positive charge. And then the Br minus can attack that carbocation to give us our final product. That's good. That's the final answer. Okay. Now let's go over the addition of X2 to alkenes. So you know how in the addition of HX of alkenes, um, we added H to one side of the alkene, and then we added X to the other side of the alkene. Like you know how this was the alkene right here? One side got an H, the other side got an X.
Mhm.
That's with the HX. If we do X2, both alkenes will have X's if we are in non-nucleophilic solvent. So let's look at an example of that. Addition of X2 in non-nucleophilic solvent, like CCl4. So let's say we have this alkene here, and we put that through Br2, CCl4. The mechanism is something like this. I'm going to draw out the Br2 explicitly like that. The alkene here, one of the carbons is going to attack that X and then kick out the other X. And as this bromine here is gaining electrons, it's becoming more positive. I mean, more negative because it's gaining more electrons. As this alkene here is losing electrons, it's becoming more positive. So this Br here is just going to come back and attack the other side of the alkene, like that, right? Where this, they add on the same side. So if that one is wedged, the other one will have to be wedged as well. And
Oh,
yeah, this right here is called the bromonium ion, right? Where both sides of the alkene attacked the bromine on the same side. It could be both wedges or both dashes. I just drew wedges in this case. From here, the Br minus that got kicked out is going to attack one of the carbons of the bromonium ion and then break open that ring like that. And this is going to be an SN2 like reaction where you notice how this bond is the one that's being broken.
mm-hmm.
That bond is the one that's going to get inverted from a wedge to a dash. The other bond that is a wedge stays as a wedge like that. And you notice how the bromines here are anti to each other. They're on opposite sides.
Mm-hmm.
This reaction undergoes anti-addition. Unlike the hydrogenation. Hydrogenation was syn addition because you notice how the two hydrogens or deuterium Ds add on the same side, syn addition.
Mm-hmm.
In this reaction here, this reaction is anti-addition because the X's add on opposite sides.
Oh, okay.
Okay. And now this is gonna go into like the relative stereochemistry, where let's give you a practice problem on this with the whiteboard. And then a lot of people had a question about this today, like the thing that he went over, relative stereoselectivity, how many stereoisomers
Mm-hmm.
there are. Let's see. Okay, so let's say, okay, in this case here, we are going to have two different products. Um, Predict those two different products in this reaction. It might help to draw the arrow pushing mechanism as well. Uh-huh, nice, nice, nice. The Cl attacks the other side of that key. And there is going to be a preferred stereochemistry for this one, because you know how in the last example I said it could be a wedge ring or a dashed ring.
Um,
In this case, there is a preferred ring that gets formed with the Cl based on what's around it.
wait, how do we know that?
Uh-huh. So, you notice how this methyl here is a wedge, which means it's
Yeah.
going towards us. That means will it have an easier time attacking on the top side or the bottom side if there's something on the top side in the way?
Oh, the bottom.
Yeah, the bottom side, which means that the preferred
Like,
ring is gonna be a dash
oh,
because
okay.
it has less steric hindrance. And steric hindrance is basically like bumping into each other, like the molecules bumping into each other. Right? And this X here with two bonds will have a positive charge. Now we bring in the X minus that got kicked out in and attack one of them. It doesn't matter in this case because we'll end up with two chlorines. Okay. Okay.
Mm,
And then what happens to this bond after this carbon gets attacked? Yeah, there you go. Uh-huh. This stays as a dash because that carbon there stays unaffected. Nothing happened to that. But this bond here was the one being attacked and get it inverted. So that dash gets inverted into a wedge. That's right. So this is one of the products. We have one more where instead of attacking this carbon, this Cl minus can attack this carbon here and then pop this ring up onto that chlorine right there. Yeah, that stays as a wedge because nothing touches that carbon, nothing touches that bond, so that stays as a wedge, right? And then this is the wedge because let's say that this Cl attacks that carbon, that will invert that dash into a wedge, and this stays as a dash, right? Where these are our two different products that we get right here.
okay.
And you notice how both of these chiral centers change, but this one stay the same.
Mm-hmm.
What would that be? Enantiomers, diastereomers, identical, meso. If some
Guys, really?
diastereomers, right, right. Because some change, but some stay the same. Not all change. This one stay the
Mm-hmm.
same because nothing touched that one. So this is diastereoselective, which is relative stereochemistry. That's what he means by relative stereochemistry because it's only relative to these two carbons right here. That there does not change.
Oh, okay.
Yeah, a lot of people had questions about that today. Like they got so confused when he was talking about that.
Yeah, I don't know.
Yeah. Does it make more sense now though?
Yes.
That's good. That's good. Tomorrow we'll do more practice problems on this, and instead of non-nucleophilic solvent, we're gonna work with nucleophilic solvents like water or alcohol, which makes things more complicated a little bit.
Okay.
But it's not that complicated. It's the same mechanism, but it's just like instead of a Cl minus, it would be like water or alcohol attacking instead a Cl minus.
Oh,
It's the same thing, but just different nucleophile. But we'll go
okay.
over that tomorrow.
Okay.
Yeah. Uh-huh. I'll post these notes and the recording to it to the calendar thing on the school. Like if you found that page, have you been able to access that page
Yeah,
yet?
I
Oh yeah,
can see
yeah.
it.
Uh-huh.
There's
Yeah.
nothing on it, but like, yeah.
Oh, there's nothing on it though. Like you don't see anything on it.
Oh wait, which one? The one from
Uh,
mine?
the one like if you go to the school website and you go to classroom, spring 2024 recordings, do you see any notes or recordings
Oh,
posted there yet? Like the week
oh,
2, week 3.
hold on. Wait,
Uh-huh.
classroom?
Yeah. Classroom, spring 2024 recordings.
Oh, I do see like the content review.
Oh, you see the concept review? Do you see beneath that week 2, week 3?
Oh, I do.
Yeah, yeah, yeah.
Never mind.
That's where I'll post the notes and the recording to this office hours.
Okay, okay.
Yeah. Uh-huh. Yeah.
Okay. Thank
I'll see
you.
you tomorrow, Maya. No problem.
Yeah, yeah, I'll see you tomorrow.
Uh-huh.
Bye.
Bye.